I'm sorry, I forgot to record this. I start to recording now. Now it's recording. Okay, so we continue with the example. So here we have a metal hoop with a radius of 6 inch, which is released from rest and 20 degrees inclined. If the coefficient of static and kinetic friction are 0.15 and 0.12 respectively. So the static coefficient of a static friction force is 0.15 and the coefficient of kinetic friction force is 0.12. So determine the angular acceleration alpha. So in this problem, as I told you, the first question is that the motion is with slipping or without slipping. So you need to consider one initial assumption and start to solve the problem using your initial assumption, and at the end of the calculation you can check your assumption. If the friction force here between the wheel and the surface was less than the maximum friction force, which is this static one, so your assumption is correct. But if you find out that this friction force is more than the static friction force, so your assumption is not correct, and you should again solve the problem, this time by using the assumption of with slipping. Okay, so here, as I told you, we start with the assumption of without slipping, so we can assume that wheel does not slip. In this case, as I told you, when you assume that there is no slipping, so we can conclude that the acceleration, the linear acceleration for this wheel, if we call it A, or here we call it A bar, is equal to R times by alpha. Here you can see R is 6 inch again, and alpha is the angular acceleration that we need to obtain this. Now the summation of the force in x direction must be equal to the mass times by ax. We know that this is the friction force. If you write the force equation in x direction, we will have the x component of the weight, which is mg times by sine theta minus f. It must be equal to the mass times by the acceleration in x direction. And again, you can write the force equation in y direction. And you know, this is x as x, if we call it x as x, and this is x as y. Okay. The x is parallel to the inclined surface and y is perpendicular to the this inclined surface. So in y direction, because there is no motion in y direction, so in the right hand side you can see we have 0. If you write the force equations in y direction, we will have the normal reactions, which we usually call it n, and also we have the y component of the weight, which is mg times by cosine theta, and theta is equal to 20 degree. Yeah, so from this equation we can conclude that n is equal to mg cosine 20. And finally, we have the moment equation. You can write the moment equation about the mass center, which is equal to the mass moment of inertia about the mass center times by alpha. When you write the moment equation about the mass center, the moment due to mg is equal to 0 because the weight is exactly on the mass center. We have the normal reaction which passed through the mass center, so it doesn't have any moment. And only this force F, if we call it F, this force will create a moment about the mass center. So the moment due to this force F is equal to F times by its radius, F times by R, and it's equal to the mass moment of inertia about the mass center times by alpha. We know that the mass moment of inertia for a hoop about this mass center, this is a ring, a simple ring, it's equal to mr squared. Okay, So here you can easily calculate and obtain the F and angular acceleration. And also we know that the maximum force, the maximum friction force is equal to the coefficient of static force multiplied by the normal reaction, which is mg cosine 20. Now you can substitute and calculate, and then we can compare. So we have three equations. The first equation is from the force equation in x direction. Second equation is the force equation in y direction. And the last one, or the third equation, is the force equation, sorry, the moment equation about the mass center. So by solving these three equations, you can obtain that alpha is equal to 11.01 and F is equal to 5.5 times by m, which m is the mass of the hoop. So this is the force, the friction force that we obtain from the initial assumption when wheel does not slip. Okay, so this is our initial assumption, wheel does not slip. So according to this assumption, we obtain that the friction force is equal to 5.5 m. But if you calculate the maximum friction force, it's equal to mu s times by n, and mu s is 0.15. Here we have, this is the mu s times by n, which is mg cosine 20. This is the n, 30.2. If you substitute, you can find that the maximum friction force is 4.53. So you can see the friction force from your initial assumption is more than the maximum friction force. So our assumption is not correct. Okay, so now we should start with the second assumption, and we need to obtain again the angular acceleration. So this angular acceleration is not correct. So let's start with the second assumption. We can consider that the wheel slips. When wheel is sleeping on this surface, so the first conclusion is that the friction force is equal to mu k times by n, or the coefficient of kinetic friction force multiplied by n, which n is again mg cosine theta. Again, you can consider this coordinate system. Okay, this is y and this is x direction. In y direction, again, you can write the force equation. So n is again 30.25. So this is the same. So F is equal to 0.12 times by n. Here you can substitute n and you can find that how much is the friction force. Now you can write the force equation in x direction. If you write the force equation in x direction, we have the weight, or mg. Okay. So the x component of the weight is mg sine theta, mg sine 20 minus F. It must be equal to the mass times by ax. Okay, we substitute here. For mg sine 20, we will have 11.01 times by m, F, which is 3.63 m, and in the right hand side we will have the mass times by the acceleration. So from here we can cancel out all of the m's and find that ax is equal to 7.38. In previous part, in previous assumption, we find out that ax is equal to r times by alpha. But here you can see that ax is equal to 7.38, and it's not equal to the r alpha. So in the next step, we need to calculate the alpha. For this purpose, again, we can write the moment equation about the mass center. If you write the moment equation about the mass center, again, the weight does not have any moment about this point. We have this force N. This force N, again, it doesn't have any moment. I don't know why this in the PowerPoint, all of the lines will have some extra lines on it. I don't know what is this. Sorry about this. So only the force, the friction force will create some moment above the mass center, and it's equal to F times by R. We calculate the F, and it must be equal to the mass moment of inertia about the mass center times by alpha. We know that F is equal to 0.12 times by N, which N is 30.25 M. Now you can substitute again, the M will be cancelled out, and you can obtain that alpha is equal to 7.26 radian per second square. So always in this type of problem, you must consider one initial assumption, which is motion without slipping. When you assume that the motion is without slipping, it means that your motion is pure rotational motion. And you can consider that the acceleration for the mass center is equal to the radius times by angular acceleration, or alpha. And then you can check your assumption. Okay, so you always must consider this initial assumption, and then if your assumption was not correct, you can assume that the motion is with slipping. And when you have the slipping in the surface, it means your motion is a general plane motion, and you will have the friction force, the kinetic friction force between the surface and wheel, and then you can calculate the linear acceleration and angular acceleration using these relations. Any question? Is it clear? Okay. Okay, we continue with another example of the plane, general plane motion. Here we have a uniform square plate, has a mass of 6 kilogram and is resting on a smooth horizontal surface in the X and Y plane. If a horizontal force P, which is equal to 120 Newton, is applied to one corner in the direction shown, determine the magnitude of the initial acceleration of corner A. So in this problem, we have a plate which is located on a smooth horizontal surface. It means that there is no friction. Okay, this plate will start to move due to this 120 Newton force. Easily we can find the acceleration for the plate, the angular acceleration and the linear acceleration, of course, for this point, the mass center. And then using the relative acceleration equation, we can find the acceleration for point A. Okay, because these 2 points are located on a rigid body. But before that, we need to obtain the acceleration for point G, and G is the mass center for a plate, and this plate has a general plane motion. I mean, when it starts to move, it will rotate and translate at the same time. So easily we can start by finding the mass moment of inertia. The motion of this plate is in X and Y plane. So the rotation is about axis Z, and we need to obtain the mass moment of inertia about the axis Z passing through the mass center. So first we obtain the mass moment of inertia about this axis Z. If we call it axis Z, we calculate the mass moment of inertia about this axis. Consider one element. This element has the dimension dx times by dy. The thickness is t and the density is rho. The distance between the axis z and the element is equal to x squared, square root of x squared plus y squared. Okay, if we call this r, r is equal to, let me show with another color, this green line, which is y. Sorry, the lines are not straight. And the blue line. So r, the red line squared, is equal to the green line squared, which is y, plus the blue line squared. So r is equal, r squared is equal to x squared plus y squared, and this is the mass moment of inertia about axis z, which is r squared times by dm, and dm is rho t dx dy. Now we can easily calculate this integral. It's very simple integral, and the domain of the integral for x is changed from 0 to 200 millimeter, and for y is again from 0 to 200 millimeter or 0.2 meter. So easily you can calculate the integral. When you are calculating the integral with respect to x, here we will have x squared, so the integral with respect to x is x cubed divided by 3, and y squared, the integral of y squared with respect to x is y squared times by x. When you are calculating the integral with respect to x, y squared is considered as a constant value. Now you can substitute, instead of x, you can substitute from 0 to 0.2, and then calculate the integral this time with respect to y. Here we will have x cubed divided by 3, which is a constant number when you are calculating the integral with respect to dy, and we will have y, then, and the integral of y squared is y cubed divided by 3. Now we can substitute the domain for y, and easily we can obtain that 0.16 is the mass moment of inertia about axis z. Again, the total mass of the plate is equal to the 0.2 times by 0.2 times by t times by rho. So easily you can simplify and find, substitute instead of rho times by t, you can substitute the mass, and then we know how much is the mass of the plate, and finally obtain the total mass moment of inertia. Now we can write the equation of motion. We will have one moment equation. The moment equation about the mass center is equal to the mass moment of inertia about the mass center times by alpha. The moment about the mass center, if we consider here, let me clear this place. Okay, if you want to calculate the moment about this point, which is the mass center, only this force P will create some moment. It will have two components, one in y direction and the other one in x direction. The y direction will be P times by sine 45, and its arm is 0.2 or 200 divided by 2, and the other one is P times by cosine 45, and again the distance or the arm is again 200 divided by 2. And because this angle is 45, you know that the moment due to P is equal to P times by 0.2 divided by square root of 2. So this is the moment due to this force. It must be equal to Ig alpha. And Ig is the mass moment of inertia about the mass center. We calculate the mass moment of inertia, mass moment of inertia about this axis Z. So Ig is equal to Iz minus md squared. You know, when you are calculating the mass moment of inertia about any axis parallel to the axis passing through the mass center, for example, when you want to find the mass moment of inertia about axis Z, it's equal to the mass moment of inertia about this axis, we call it G, plus md squared. But this time we have the mass moment of inertia about axis Z. We want to obtain the mass moment of inertia about the mass center. So it's equal to Iz minus md squared. And again, d is this distance, the distance between axis G and axis Z, which is equal to this length is exactly equal to in this triangle. Again, it's equal to 0.2 divided by 2 squared plus 0.2 divided by 2 squared, which is equal to 0.02. Okay, this term, and we calculate the Iz, which is 0.16, and d squared is equal to 0.02 and times by m, which is the mass of the plate. Now we can substitute for the mass, and finally we can calculate the mass moment of inertia about the mass center, which is 0.04. Now you can substitute here and finally calculate the angular acceleration for the plate. The next step, we need to write the force equation in x direction and in y direction. If you write the force equation in x direction, we will have a summation of the force in x direction is equal to m times by ax, and in the x direction we only have p times by cosine 45, and in y direction again the summation of the force must be equal to the mass times by the acceleration in y direction. Again in y direction we only have p times by sine 45. So easily you can calculate the ax and ay, or the x and y component of the acceleration. So in this step we calculate the angular and linear acceleration for the plate from the kinetics of the problem. The next step, we need to obtain the acceleration for this point A using the acceleration of the mass center, because these data ax and ay, this is the ax and ay, are the acceleration for the mass center. Of course, the angular acceleration is for the whole rigid body, but the linear acceleration ax and ay are only for the mass center. So the next step, we need to obtain the acceleration for point A using the acceleration of the mass center. Is it clear so far? Any question? Okay. So as I told you, the next step, we need to obtain the acceleration for point A here, this point. So we can consider a rotating coordinate system at point G or a relative coordinate system at point G. If we assume here at the mass center, we assume a relative coordinate system, we can write the acceleration of point A with respect to the acceleration of point G. Here, this is the absolute acceleration for point A. This is the acceleration of the mass center. This is the relative acceleration between point A and G. And because this is a rigid body, we know that the relative acceleration between A and G is equal to 0. This is the alpha, or the angular acceleration for the system. RAG is the position vector of A with respect to G. Omega cross RAG, which omega is the angular velocity of the plate or of the coordinate system. And finally here we have V relative, again the relative velocity between point A and G. RA with respect to G, if you assume here we have a coordinate system, this is X and this is Y and X. This coordinate system, if you find the position vector of point A, this is the position vector. Sorry. The position vector of point A, this point, will be 200 millimeter in X direction divided by 2, and in Y direction is 200 again divided by 2, or 0.1 I and 0.1 J. So this is the RA with respect to J. And another point, at this instant, when this plate start from rest, at this instant, omega is equal to 0. It means that the angular velocity of the relative coordinate system, or this X and Y, the blue coordinate system, is equal to 0. So this term is 0. Here the relative velocity is 0. And here the relative acceleration is 0 as well. So A, or the acceleration of point A, is equal to the acceleration of point G plus angular acceleration cross RA with respect to G. So AG is the acceleration of the mass center. We calculate AX and AY. This is the AX and this is the AY. The alpha, which is calculated in previous slide, is 424.2 in Z direction cross by RAG, which RAG is 0.1 I and 0.1 J. So easily you can substitute here and simplify this equation. We have a cross product equation. In this cross product, we have K cross I, which K cross I is J, and we have K cross J, which is minus I. So you can simplify this equation, and finally the acceleration of point A will be calculated. So we divide the problem into two main steps. The first step, we calculate the acceleration of the mass center and the angular acceleration of the plate. And in the second part, in the second step, we use the kinematic relations, and we consider a relative coordinate system at the mass center and find the acceleration of point A using the acceleration of the mass center. Okay, any question from this example? Is it clear? If you don't have any question, we can wrap up this session and continue for the lecture in the next week.